Hello everyone, welcome to the YouTube channel Thermal Engineering MODULE-3. This is the course on Turbomachines, which is exclusively made for the VTU students, Mechanical Engineering, 5th semester. Okay, in the today's lecture, we will see the very important topic on module number 3, that is steam turbines. And the topic of today's discussion is a condition for maximum blade efficiency of a single stage impulse turbine. Condition for maximum blade efficiency of a single stage impulse turbine. So first we will try to study what is the single stage impulse turbine, okay, and after that we will see how to draw the combined velocity triangle for a single stage impulse turbine. Thereafter we'll go with the derivation, that is condition for maximum blade efficiency of a single stage impulse turbine. Okay, as the name itself indicates, in this we have one stage, single stage, which comprises the two rows. This is a first row and this is a second row. Okay. In the first row, we have the set of nozzle, a completely well insulated nozzle. And in the second row, we have the set of moving blades. The set of moving blades here. These are the moving blades. The steam at high pressure, high temperature, the superheated steam, it expands into the nozzle, where at the expense of enthalpy, the jet with high kinetic energy, it is expelled out from the nozzle. It is expelled out from the nozzle. With the velocity v1, it hits the moving blade, and due to the change in the velocity as well as the change in direction of motion, there is a momentum exchange between the high velocity jet and the rotating blade, and hence we can produce the mechanical energy in the form of rotation. So this is a very basic, simple discussion on single stage impulse turbine. Okay. Now, how the pressure and velocity varies along the stage. Okay. So here, first we'll see how the pressure varies, and next we'll see how the velocity varies. Let me use the dotted line for pressure and continuous line for velocity. The high pressure, high temperature steam, let us take it as PI, the inlet pressure of steam. When it expands into the nozzle, the pressure gradually reduces. It reduces, and as it flows over the moving blades, the pressure remains constant. And that is equals to P naught, which is known as the condenser pressure. Okay. Now, as far as the velocity is considered, the velocity in nozzle, it increases, and as it moves over the moving blades, the velocity gradually decreases. So this is the variation of velocity along the both the rows or along the complete stage. Okay, so this is a very basic and simple discussion on single stage impulse turbine. Now we'll see how to draw the combined velocity triangle for a single stage impulse turbine. Okay. So here, this is a common base U. This is the common base, that is U here. The tangential velocity of the blade or tangential velocity of the runner. Okay. V1 is the absolute velocity. V1 is the absolute velocity or velocity of the steam which is coming out from the nozzle, and it is of course inclined at an angle alpha 1 with respect to horizontal. Now here VR1 is nothing but the relative velocity component at the inlet. Now the vertical component of absolute velocity is This is the vertical component of absolute velocity, that is Vf1, which is known as the flow velocity component. Which is known as the flow velocity component. And here beta 1 is the angle, relative velocity at the inlet, relative velocity component at the inlet, which makes an angle beta 1 with respect to horizontal. So this is the complete inlet velocity triangle. Now how to draw the outlet velocity triangle? This is the outlet velocity triangle. Here VR2, the relative velocity component at the outlet. This is V2, the exit velocity from the moving blades, and the vertical component is Vf2, the flow velocity component at the outlet, and V2 makes an angle alpha 2 with respect to horizontal, and beta 2 is the angle made by VR2 with respect to horizontal. This is the tangential velocity u, and this complete vector, that is the horizontal component Vu1. Vu1 stands for the tangential velocity component at the inlet. I repeat, Vu1 stands for the tangential velocity component at the inlet. Similarly, the tangential velocity component at the outlet is Vu2. Vu2. Let us name all the corners A, B, C, D, E, and F. Consider a single stage impulse turbine. The combined velocity triangle. Is shown in figure. Above. Okay. Shown in figure above. Okay. Now here, our main aim is to derive or develop the condition for maximum blade efficiency of a single stage impulse turbine. Now here, the efficiency is defined as a ratio of, listen here carefully, efficiency or the blade efficiency is defined as a ratio of work done per kg of steam by the runner divided by the kinetic energy supplied, or the specific kinetic energy supplied to the runner. Okay, so both we will derive separately, and after that we'll substitute in the blade efficiency equation to derive the condition for maximum blade efficiency. So this will be more clear if you derive this equation systematically. So let us focus here. Work done, we know that work done per kg of steam, we know that U by Gc into Vu1 plus Vu2. This equation we have got in the module number 2, that is in Euler's turbine equation. This equation is popularly known as the Euler's turbine equation. Okay. Now here, this equation can also be written as U delta Vu divided by Gc. U delta Vu divided by Gc. So this is a very basic equation for work transfer or work done per kg of steam by the runner. Work done per kg of steam. Work done per kg of steam. Okay. Let us keep it as equation number 1. Okay. Now we know that delta Vu equals to, listen here carefully, the algebraic sum of Vu1 and Vu2. The algebraic sum of Vu1 and Vu2 is nothing but delta Vu. Here. Okay. The delta VU can also be written as VU1 plus VU2. Okay, or minus it means. Sometimes it may be minus, because if the direction of VU1 and VU2 are opposite to each other, they may be away from each other or they may be towards each other. If they are opposite to each other, if the direction is opposite, then we are supposed to take the positive sign here. And if they are in same direction, we are supposed to take minus sign, that is negative sign, right? Okay. Now the delta VU is the total distance, that is V to E is the delta VU. Now the delta VU can also be written as BC plus CE. BC plus CE. Now here BC can also be written as VR1 cos beta 1. VR1 cos beta 1. See here. Cos beta 1 from the triangle ABC. From the triangle ABC, cos beta 1 is base is BC divided by hypotenuse is VR1. Or BC is equals to VR1 cos beta 1. VR1 cos beta 1. Similarly, from the triangle FEC. From the triangle FEC, I can write cos beta 2 equals to CE by VR2, or CE equals to VR2 cos beta 2. So ultimately I can write delta VU is equals to VR1 cos beta 1 plus VR2 cos beta 1. See here, VR1 cos beta 1 plus VR2 cos beta 2. VR2 cos beta 2. Let us take VR1 cos beta outside the bracket. VR1 cos beta 1 outside the bracket. So we are left with 1 plus VR2 cos beta 2 by VR1 cos beta 1. VR1 cos beta 1. Okay. Let VR2 by VR1 is equals to CB. CB is the blade coefficient. CB is the blade coefficient, which is the ratio of relative velocity component at the outlet, that is VR2, divided by relative velocity component at the inlet, that is VR1. Again, let us take this ratio as CB, that is blade coefficient, and similarly cos beta 2 by cos beta 1 as K, some constant K. Now here I can write delta VU as VR1 cos beta 1 as it is into 1 plus CB into K. 1 plus CB into K. Now here VR1 cos beta 1 can also be written as VR1 cos beta 1. It can also be written as VR1 cos beta 1, that is BC. BC can also be written as total distance VU1 minus U. VU1 minus U. Okay? VU1 minus U. Now here from the triangle ABD, cos alpha 1 equals to VU1 by V1. From triangle ABD, cos alpha 1 equals to VU1 divided by V1, or VU1 can also be written as V1 cos alpha 1. So therefore VR1 cos beta 1 is equals to V1 cos alpha 1 minus U. V1 cos alpha 1 minus U here. Let us substitute VR1 cos beta 1 here as V1 cos alpha 1 minus U. So therefore I can write delta VU equals to, so in place of VR1 cos beta 1, V1 cos alpha 1 minus U into 1 plus Cb into K as it is. 1 plus Cb into K as it is. Now, by the definition of specific speed, which is a ratio of tangential velocity of the blade to the absolute velocity of the steam. Okay, so we know that by the definition of, okay, so before that, let us substitute this delta VU in equation number 1 using above delta VU in equation 1. In equation number 1. So I can write work done per kg of steam. Work done per kg of steam. Work done per kg of steam. It can be written as U as it is, U by Gc as it is, U by Gc into V1 cos alpha 1 minus U into 1 plus Cb into K as it is. 1 plus Cb into K as it is. Okay. Now here, speed ratio. You can write the speed ratio, that is phi equals to, this we have learned in the module number 1, that is introduction to turbo machines. Okay. So phi, it can also be written as U by V1, where U is the tangential velocity of runner divided by V1 is the absolute velocity of steam at the inlet or the exit of the nozzle. V1 is the absolute velocity of steam at the exit of nozzle, or it is the velocity of steam at which it hits the runner or the runner blades. Okay, so that is V1. Fine. Now here U can also be written as phi into V1. U can be written as phi into V1. Let us substitute U equals to phi into V1 in equation, in this above equation. So therefore, work done per kg of steam, work done per kg of steam can be written as U is phi into V1 by Gc as it is into V1 cos alpha 1 minus U is phi into V1 into 1 plus Cb into K as it is, into 1 plus Cb into K as it is. Or let us take V1 outside the bracket in this equation. Let us take outside the V1 outside the bracket. So I can write here work done per kg of steam. So phi into V1 square divided by Gc into cos alpha 1 minus phi as it is into 1 plus Cb into K. 1 plus Cb into K. This is the work done per kg of steam. Okay, work done per kg of steam. Now here, we know that the blade efficiency or the diagram efficiency, it can be written as work done per kg of steam divided by the energy supplied per kg of steam. Okay, so let me write here blade efficiency, it can be written as eta B equals to work done per kg of steam divided by kinetic energy supplied per kg of steam, kinetic energy supplied per kg of steam. Okay. Now this can also be written as work done per kg of steam is equals to is divided by the kinetic energy supplied. We know that kinetic energy equals to half mv square. So as we are taking per unit mass, so I can write it as v1 square divided by 2gc. v1 square divided by 2gc. So this is the specific kinetic energy supplied to the runner. Okay. Now this is the efficiency. Now let me continue here. Okay. So efficiency, the blade efficiency, it can be written as so work done per kg of steam. Already we got the equation, that is 5 into v1 square divided by gc into cos alpha 1 minus 5 into 1 plus cv into k. 1 plus cv into k whole divided by v1 square by 2gc. v1 square by 2gc. So gc will get cancelled. v1 square will get cancelled. So we are left with eta b equals to, so take 2 to the numerator, 2 5, 2 just multiply the 5 with entire bracket. So 5 cos alpha 1 minus 5 square into 1 plus cv into k as it is. 1 plus cv into k as it is. So this is the blade efficiency. This is the equation for blade efficiency. Now here ultimately what we want? We want the condition for maximum blade efficiency. A little consideration shows that here cv is constant, k is constant, and alpha 1 is also constant. The only variable is phi here. Let us differentiate this equation with respect to phi and equate it to 0. In order to get the condition for maximum blade efficiency, we have to differentiate this equation with respect to phi and we have to equate it to 0 to get the condition for maximum blade efficiency. Okay. Now let us rub this portion so that I can get the enough space to derive the equation. Okay. Now let us keep this as equation number 2. To get the condition for maximum blade efficiency, differentiate equation number 2 with respect to phi and equate it to 0. Okay. So that is the differentiation of blade efficiency with respect to phi equal to 0. So the differentiation of this term, okay. Kindly write down the differentiation of this term 2 as it is into the differentiation of phi cos alpha 1 is only cos alpha 1 with respect to phi minus phi square differentiation is 2 phi into 1 plus cv into k as it is. Of course, we have to equate to 0 because 1 plus cv into k is a constant term. Here in this equation, 1 plus cv into k will never be equals to 0. It will never be equals to 0. So we are left with cos alpha 1 minus 2 phi. It can be equals to 0. So after rearranging, I can get phi equals to cos alpha 1 divided by 2. So this is the condition for maximum blade efficiency of a single stage impulse turbine. Many times it has been asked in the previous year competitive exams like RRB, railway exams, SSC, JE exams. What is the condition for maximum blade efficiency for a single stage impulse turbine? So speed ratio phi should be equals to cos alpha 1 divided by 2, where alpha is the nozzle angle. So this is a very important concept as far as your competitive examination point of view. Okay. Now we have to substitute this condition in equation number 2 to get the final equation for maximum blade efficiency. Okay. Using the above condition, in equation number 2, so I can get the maximum blade efficiency is equals to 2, wherever the phi is there, you have to substitute cos alpha 1 by 2. So phi is there, cos alpha 1 by 2 into cos alpha 1 minus phi square is there, cos square alpha 1 by 4 into 1 plus Cb into K as it is. 1 plus Cb into K as it is. Okay. So the maximum blade efficiency is, so just multiply. So we'll get cos square alpha 1 by 2 minus cos square alpha 1 by 4 into 1 plus Cb into K as it is. Okay. Take the LCM and do the simplification. So I can get, after that we cancel 2. So finally I can get, so 2, the 4 will be LCM. So 4, 2 will get cancelled. So here we are left with cos square alpha 1 into 1 plus Cb into K as it is. Now here, if we consider the most ideal condition, that is no frictional losses, then the VR1 will be equals to VR2. If VR1 is equals to VR2, then CB will be equals to 1. CB will be equals to 1 if VR1 is equal to VR2. Similarly, if we consider the equiangular blades, if the blades are equiangular, that is beta 1 equals to beta 2, so I can write K equals to 1 for equiangular blades. Is that clear? So K equals to 1 means beta 1 equals to beta 2, that is equiangular blades. So if we use these two conditions, okay, here 4 is LCM, okay, here I'll get 2. Okay. So after cancelling, I'll get divided by 2. After cancelling 2, I'm sorry. After cancelling, we'll get cos square alpha 1 by 2 here. Okay. Now in this, let us substitute these two conditions. Okay. So cos square alpha 1 by 2 into 1 plus 1, that is 2. 2 will get cancelled. So we are left with the maximum blade efficiency equals to cos square alpha 1. So this is the final equation, that is a maximum blade efficiency for a single stage impulse turbine. This is the condition, or this is the final equation for maximum blade efficiency of a single stage impulse turbine, and this is the condition for maximum blade efficiency. Okay, hope this is clear. Watch this video completely. If you have not followed this derivation, kindly watch it again and again, so you'll get the concepts. Okay, so further, if you have any doubts anywhere, you can put your comments in the comment box, or else you can put your personal queries on the personal WhatsApp number, that is 98865390074. This is the WhatsApp number. So if you have any queries, you can contact on this number. Okay, this is the WhatsApp number. So please don't forget to like, share, and subscribe the channel. Thank you. Thanks for watching this video, and have a nice day.